This week, we're going to talk about the concavity of functions. So it's essentially what we were doing last week, but instead of working with a first derivative, it's a second derivative. But it's pretty much the exact same thing. So we're going to start off by talking about the definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I when f prime is increasing on the interval and concave downward on I when f prime is decreasing on the interval. So we want to know when the derivative is increasing or decreasing. So that's what I'm saying. It's kind of like what we did last week, because last week we were working with the first derivative to figure out when the original function was increasing, decreasing. But now we're going to use the second derivative to talk about when the first derivative is increasing or decreasing. And then we have theorem 3.7, which is on page 189 in the textbook. And it states, let f be a function whose second derivative exists on an open interval I. So we have to make sure that the derivative exists to begin with. If the second derivative of x is greater than 0 for all x's in the interval, then the graph of f is concave upward on the interval I. I'm going to silence my phone. Sorry about that. If f double prime is less than 0 for all x in I, then the graph of f is concave downward on I. So to apply this theorem, we have to locate x values at which the second derivative is equal to 0 or the second derivative does not exist. Then we use that to create our intervals, then we just test it out like we were doing before. All right. So we're going to work with a very nice and easy polynomial to kind of just dip our toe in the water. Then I'll show you a little bit of a more complex one. Okay? So if I have f of x is equal to x to the fourth minus a 4x cubed, then I can say that the derivative of that, there we go, would be 4x cubed minus 12x squared. Now I need the second derivative, so do it again. 12x squared minus 24x. All right. So the important part is if I'm going to try to figure out the concavity, I need to take my second derivative and locate the values of f, look at the x values at which f double prime of x is equal to 0 or the second derivative does not exist. So I'm going to go and look at my derivative. It's a polynomial, so I know that it will always exist for all real numbers. I don't have to worry about that second condition for this, but I do need to figure out where the second derivative would equal 0. So I want this to equal 0. So doing a little bit of light factoring, we can say it's a 12x times an x minus 2 equals 0. X would have to be 0, or x would have to be 2, just by solving this polynomial. So I'm going to leave this in this factored form, and I'm going to figure out the intervals and do all that by using the factored form, because I'd rather think about what I'm multiplying than actually find the number itself. So bear with me, see if you guys have questions, okay? All right. So drawing the number line, I know I should put uh, 0 and 2 as, we're not going to call them critical numbers because critical numbers only apply to the first derivative, and these are something else. Can I? Yeah. Okay. Yeah, let's do it. We're going to call these new values points of inflection. Do I want to do it that way? No. No, these are not points of inflection. Points of inflection are similar to this, but they have slightly different conditions. So for now, they're not critical numbers, but they kind of act like critical numbers, except they're dealing with the second derivative. So that's the important distinction. It's the second derivative now. Okay, so let's test out a number, let's say, I don't know, -1. If I plug -1 in here, I'm going to get 12 times a negative. 1 will be a negative. -1 minus 2 will also be a negative. Negative times negative will actually give me a positive. Positive. Okay. So I have that there. Now I'm going to take another number. This time would be between 0 and 2. So let's say 1. Or replace that x with a 1. That would give me a positive number. 1 minus 2 would give me a negative number. Positive times negative gets me a negative. Keep it going. Let's say it's now 3. 12 times a positive 3 will be a positive number. 3 minus 2 will be a positive number. So I'm going to get a positive because positive times positive stays positive. Okay. So based off this number line, here's what I can say. Whenever for the concave upwards, it's wherever my second derivative is positive. So I can say from negative infinity to 0, or from 3 to positive infinity, that's where it's concave upwards. All right. And because we had a negative value between 0 and 2, from 0 to 2, my graph would be concave downward. And that's all, at its core, that's all you have to do. But let's try a more difficult